Hello, Dr. Darshan Delan and everyone of our class. My name is Siddham Vamsi. I'm excited to share the first part of our team's project for predictive analytics. Our project, we titled it as Motor Vehicle Crash Injury Severity Analysis. Over the past 3 weeks, we have been working on this project and we are Team 6. Next, please. I'm Siddham Vamsi.
I'm Carson Jones.
I'm Jayashree.
I'm Saidavi.
Yeah, we four have been working on this project on understanding what factors contribute most to the major injuries in the automobile industry. So today I will walk you through the project overview, business understanding, and data understanding stages of our work. Next, please. So this is our agenda. We will go through overview, business understanding, data preparation and modeling, testing and evaluation, deployment and conclusion in your presentation in the next 20-25 minutes that we're going to take. Next, please. So when you come to overview, the project statement is simple but powerful. Using crash data and NIME analytics platform, we applied the CRISP-DM methodology to predict whether a crash would likely cause a minor injury or not. This is simple and powerful project statement. Just a quick note on CRISP-DM for all of you. It stands for Cross Industry Standard Process for Data Mining. It's basically a structured 6 phases of framework that data scientists use to make sure the projects stay organized, starting from understanding the problem, preparing data, modeling, evaluating, and results, and also deploying solutions. Now, if you think why CRISP-DM, because it's very flexible and it lets you move back in your project when there is any changes, when you know about new things in your data. We also choose NIME because it's an open source and low code tool that help us to get on to work with this project with more kind of what do you say, it's an easy thing for us to do. So in simple words, our goal is to figure out what factors that predict serious fatalities in crash injuries and build models that can actually forecast outcomes based on crash related information. Next, please. So business understanding, we usually have business understanding for purpose, questions, and success criteria to discuss all of these things. So let's talk about this. Our main goal was to predict severity of injuries in automobile crashes using machine learning technologies. But more importantly, the purpose behind the project was to help policymakers, emergency services, transportation authorities, making things smarter, faster, and more data driven solutions. Whether it's about designing safe roads, deploying first responders more efficiently, or making better traffic safety policies. We focused on answering two major questions. First, what factors contribute most to major injuries in crashes? Second, can we build a model that accurately anticipates injury outcomes just based on crash related data? And of course, no project is complete without success criteria. For us, success criteria and success meant achieving higher predictive accuracy and reliability, which is meaning it the model actually works well in real world situations too. And the second, clear interpretability, meaning it's not just a black box. We understand what factors matter the most for us and for the project as well. Third, practical usefulness, meaning the model's insights could actually be applied to improve traffic safety strategies and emergency response planning. So everything we did from this point onward was aligned to the goals like accuracy, interpretability, and real world impact. Next, please. So moving into our data understanding, which is a critical part of the project, we worked with four data sets from the crash report sampling system CRSS collected by NHTSA between the date of 2016 and 2019, but we have used 2019 data. Each data set serves a different purpose for us in the project. The vehicle data set, it contained about 84 columns and 94 and nearly 95,000 rows covering information like vehicle type, vehicle weight, point of contact, and safety features like airbags. Second is accidents. The accident data, it has 46 columns and around 55,000 rows were there providing details about crash itself, which means date, time, location, road surface, lightning and weather conditions. Third being person's information, which has 54 columns and which is around 1,31,000 rows. It describes about individuals involved in it, like, driver's age, driver's gender, driver, whether he is using seatbelt or not, and, the injury outcomes from it. The fourth being distract dataset, which has 11 columns and around 94,700 rows in it. It captures distraction related information of the driver, which whether whether the driver was texting, whether he was adjusting controls, and he was talking to the passengers and all those kind of things. Next, please. Now, the thing is, the most important thing is, how did we bring all of these together? We used KNIME. We used various nodes that are available in the KNIME. The data set that was given to us is in SAS model, so we used SAS nodes. So we also kind of performed full join to join all these data sets. So let me tell you why we use full join in this project. No, because we wanted to preserve as much as information that is available and also possible for us to make the accuracy level more accurate, and also it also makes us not to lose the rare cases might have been weakened our ability to find important patterns. After merging, we had a very rich, very detailed, and with very detailed data set which allowed us to ask deeper questions about injury severity. Next, please. So and also one more important thing, for our analysis we excluded I'm sorry, and also we excluded missing values in our data set. We used median and mean to impute them. So the dependent variable, the target variable for our data set is injury severity. We have been that in major and minor. And and going forward, I'll ask my friend Jayashree to take on from here. Thank you. You are on mute.
Yeah. Thank you, Vamshi. So as a part of data preparation, in this data set, particularly like this data set contained information about on the weather, drive factors, on car details, as well as injury and road information. There were not many, but there were like columns that had missing values. To mitigate that missing values, at least for numerical ones, we replace the missing values with a mean or median, depending on the missing values and how we are going to handle it. And the next one is to properly process our dependent variable, which is the injury severity. So for the injured severity, we started like binning and excluded like the other values from like say 1 to 5, so that they don't like overly affect our dependent variables. So 1 to 3 have been binned to our minor severity, and the remaining values like 4 to 9 have been binned into the major severity. Can you move on to the next one, please? So there are like few variables that we derived from the other variables that we chose. One is the vehicle age, which was derived from the mod year. So the basically is like it is like removing like subtracting like the current year with the mod year to actually determine the age of the vehicle. And the other one is the overspeed. The reason why we took is like there could be a big influence. We thought like there could be a big influence of how the overspeed is going to play on our dependent variable. So that was derived from the travel speed and the speed limit in that particular area of the accident. Can you move on to the next one? We also selected 34 additional variables that potentially would determine the severity of injury in an accident. So those included driver factors, which are age, drug and alcohol, environmental factors such as the weather conditions, light conditions, surface conditions, and accident factors such as the manner of collision and how deformed the vehicle was. You move on to the next one. So these are the total variables that we had taken as a process of data preparation. And can you move on to the next one, please? So data filtering as considered like data filtering, only like a minimal filtering was done because like as Vamshi said, like we had to retain as much information as possible with our data set. And as for the body type, to homogenize the body type, we filtered values from we retained values from 1 to through 49 that eliminated like motor vehicles, ATVs, heavy and commercial vehicles from our data set, and also had to filter like a model year between 1990 to 2023, which eliminated like 999, which was given as entered as like unknown in the data set. Rule engines were also used to group the data set and process it. Can you move on to the next one, please? So we then moved on to binning. We decided to bin the 14 of the 34 variables. So binning is a process used to transform the continuous numerical values into categorical values by separating them into bins. For example, we binned the we have been like day week, say day week, we bent into like day weekend and weekdays so that we could get a like a overview of what day or what kind of week influenced more like severity of our accident. Can you move on to the next, please? So for our project, we decided to use equal size sampler. So in equal size sampler, which is basically like undersampling or severity data, and it is used to make the dependent variable to be equally distributed. The next ones are one-to-many, and normalizing is used for logistic regression and neural networks in our modeling. So one-to-many is basically convert the nominal data to numerical data for the model that cannot use the nominal data. And normalizing is like covering or like bounding every range into a set range. For example, we used like normalizing to from 0 to 1, and this prevents like larger values from overpowering the minute and minuscule values that we have. Can we move to the next one, please? So yes, that is with the data preparation. I'll pass out to Carson to continue.
Yes, so next we have our modeling section. We started first with our decision tree because we decided to split it into two different ways. You could either go set-based model, which works well with categorizing stuff, so it can group stuff very well, like injury levels, for example, or there's numeric-based models, which are for more continuous numbers and mathematical relations, and each model will work differently with each different type of data set. And to our right, you can see our decision tree hierarchy, figuring out which variable is more important and what determines your injury severity level. And next we have our random forest. It's pretty much like a decision tree. It combines your outputs and it can ensemble approach and will reduce your model variance, leading to more stable and accurate predictions. For the injury severity task, random forest improved generalization to unseen data compared to a single decision tree. We also have another variable importance graph, which is easier to see. As you can see, the ejection miss is probably one of the most important factors going into your injury severity level. As you go down, day of the week does not matter as much as being ejected from your vehicle would be. It helped figure out what factors influence crash outcomes, just from not even for your model, but for a human just looking at it. We have our next model, the naive Bayes model. It assumes that all attributes are conditionally independent, which really changes how it will work out. The assumption limits performance, especially with complex, high-dimensional data where features are often correlated. In our case, variables like driver distraction and ambient lighting were not independent, which could mislead the model prediction, but we'll get to that when we get to our evaluation section. Our next one is our gradient boosted trees, which is an ensemble method that builds a strong predictor by combining multiple weak learners sequentially, and each new tree focuses on correcting the errors made by the previous trees. Unlike the random forest, which average independent built trees, gradient boosted trees in a sequence to minimize prediction errors. I'm also not sure if this was mentioned in our pre-processing, but we also made sure to partition our data. That way you won't have weird corrections later on. We also did a logistic regression, which is a great baseline model. It's a pretty basic one, and a lot of it uses it. It estimates outcome probabilities by applying a logistic function to linear combination of predictors. It's pretty good at categorical variables like your seatbelt use, your distraction, illumination, and everything else. Our final one, I think, is our neural networks, which was used to detect, it's actually MLP on this one, a feed-forward architecture with a single hidden layer was employed. Input features were normalized using min-max scaling or z-score normalization to improve convergence. And next is our evaluation.
Yeah, coming to the evaluation, once the models were built, the next step was evaluating their performance. We compared 6 classical models to see which one predicted injury severity most accurately. To ensure a fair comparison, all models were trained on 70% of the data and tested on the same 30% of the data. We used metrics like accuracy, sensitivity, and specificity, and the ROC value. The next one. Out of all the models, gradient boosted tree got the highest ROC value of 0.79, followed closely by logistic regression and random forest. Well, models like naive Bayes and decision tree struggled a bit, especially with complex patterns. Gradient boosted tree and logistic regression constantly delivered strong and best predictions. In summary, evaluation phase confirmed that these two models were our best choices for predicting major injuries with the confidence. And the next one. Once we Once we added the best model, the next step was deployment. During the deployment, there are three key determinants of injury severity. Ejection significantly increases the risk of major injuries, while proper use of restraint system greatly reduces it. By forcing on these factors, our deploy model can help guide safety improvements, public awareness efforts, and injury prevention strategies. And the next one, we created a NIME workflow that processes new crash data in real time. The workflow applies the same data cleaning and transformation steps we used during the training. Then the trained gradient boosted tree model makes a predictions like will the injury be major or minor. Like this kind of deployment could be integrated into emergency responses or traffic monitoring tools. For example, if the crash data from sensors or public reports can be fed into the system instantly, authorities can could prioritize ambulance dispatches or reroute traffic based on the injury severity and predictions. Deployment also means thinking about the future. The model will need to update over time and driving behaviors, vehicle technologies, and road conditions. And the next one. To wrapping it up, the project really showed how machine learning can make a real difference when it comes to traffic safety. By analyzing detailed crash data and building several prediction models, we were able to identify key factors that contributes things like vehicle age and the type of collision, seatbelt usage, and even environmental conditions. Our best model uh, is gradient boosting tree gave the strong and reliable predictions. And the deployment opens up a lot of responsibilities for improving emergencies and responses, and also road safety measures. Moving forward, there is a room to make this system smarter and faster. But even right now, it shows how powerful data-driven decision making can be, save lives and making our roads safer. And the next one. Thank you.